Welcome back to the Explainer. Let's jump right in and pick up exactly where we left off, with that massive cliffhanger from our last session on linear transformations. We learned that some matrices have a clean undo transformation, called an inverse, while others squash space completely flat, completely destroying information. But finding out which is which by going through the whole inverse calculation was, honestly, an exhausting process.
So here's the core problem. How do we know if a matrix just totally collapses our data, making an undo impossible, without actually grinding through all the complex math first? Like, is there a cheat code? A simple, single early warning system? Well, yeah, there absolutely is. It's called the determinant.
Here's our roadmap for today. We'll hit the invertibility cliffhanger, dive into the geometry and the formula, run through a simple numeric example, decode positive, negative, and zero values, touch on 3D volume and AI uses, and then wrap up. All right, Section 1, the invertibility cliffhanger, finding the cheat code for matrix inverses.
As you might remember, multiplying a matrix by its inverse gives us the identity matrix, effectively hitting the undo button. But some matrices squash 2D space down into a single flat line, permanently destroying information. When that happens, you genuinely cannot tell where two different points used to be, because they are now crammed onto the exact same crushed line. We need a magic number to warn us before that collapse happens.
Moving to Section 2, Geometry and the Formula, Visualizing Area and Deriving AD minus BC. To find that magic number, we really need to picture the physical space. Imagine a basic unit square on a dark grid getting stretched out into a slanted parallelogram. The determinant is really just asking one simple question: how much bigger or smaller did that area get? If your starting square had an area of 1 and your new shape has an area of 3, boom, your determinant is simply 3. It's literally just a scaling factor for area.
So think about this for a second. If a transformation shrinks that unit square down to exactly half its original area, what do you think the determinant is? Yep, you guessed it. It's 1/2. See, the determinant only cares about the final area. It doesn't care about the actual outline or the specific shape itself.
So how do we actually calculate this thing? Well, by tracking where our basic right and up basis vectors land. Using the columns of a 2x2 matrix, the area of our new parallelogram works out perfectly to AD minus BC. The first column gives us A and C. The second gives us B and D. That little short formula, that is our cheat code.
Okay, Section 3, a simple numeric example, crunching the numbers for a 2x2 matrix. Here's the exact matrix we used in our last explainer, broken down into our 4 variables, A, B, C, and D. Our first column is 2 and 1, and our second column is 1 and 1.
Let's run the math. It's super easy. We just multiply the diagonals and subtract. Step 1, A times D. That's 2 times 1, leaving us with 2. Step 2, B times C. That's 1 times 1, which is 1. Step 3, we subtract 1 from 2, leaving us with a determinant of exactly 1. And what does a determinant of 1 actually mean? It means this transformation perfectly preserves area. Nothing was magically created and nothing was lost.
Section 4, Positive, Negative, and Zero. Decoding the signs of the determinant.
Now, obviously, an area can't be a negative number, right? That makes no physical sense. So a negative determinant is quietly tracking that your space just got flipped, kind of like a mirrored reflection. A determinant of -1 means the area is perfectly preserved, but the orientation is totally reversed. It's like your right hand becoming a left hand. No amount of normal spinning or rotating is going to make it match your right hand again. And here's the big reveal, the whole point. If your determinant is literally 0, your 2D space has been totally crushed down onto a flat line, or even a single dot. Space is collapsed, information is completely gone, and mathematically, an inverse is absolutely impossible. You don't need to try and calculate the whole inverse anymore to see if it works. You just check if the determinant is 0. Boom, you're done.
All right, Section 5, 3D volume and AI uses, scaling up to 3 dimensions and machine learning. Let's expand this outward. The exact same rule applies as we jump up in dimensions. In 3D space, instead of measuring how area changes, the determinant measures how volume changes. So, if a 3D transformation squashes a cube completely flat into a 2D sheet, the volume becomes 0. Once again, information is completely lost, and you cannot undo the transformation.
Now, to be totally honest with you about modern AI, large language models mostly just rely on standard dot products and matrix multiplication during their training runs. They aren't calculating determinants nonstop. But
Determinants are absolutely vital whenever an advanced machine learning system needs an ironclad guarantee that it can recover its original information. We're talking covariance matrices and stats, controlling the spread in multivariate Gaussian distributions, and they are heavily used in Jacobians for tracking probabilities in generative models called normalizing flows.
Finally, Section 6, Wrap Up and Next Time. Let's summarize our core rules.
Okay, let's lock in our core takeaways. Determinants act as a scaling factor for area in 2D or volume in 3D. The formula for a 2x2 matrix is simply AD minus BC. Negative determinants, those mean a flipped orientation. And crucially, a determinant of 0 means space completely collapsed and the matrix has absolutely no inverse. Basically, this one single number tells you instantly if your transformation is safely reversible or if it just crushed your data into oblivion. So, we've seen how matrices stretch, flip, and squash space. But consider this. Even when a transformation perfectly preserves area, are there special, unique directions in space that survive completely untouched? Like directions that only get stretched or shrunk, but never actually bent away from their original path. Figuring out those untouched, unrotated directions is going to lead us right into our next explainer on eigenvalues and eigenvectors. Until then, keep exploring.